Have you ever stopped to think about how your phone charger works? You know, how it takes the power from your wall and turns it into something your device can actually use? Well, the secret is this tiny but incredibly important little component. Today, we're diving into the magic of the PN junction diode.
So let's frame this whole thing with one simple question. How in the world do you build a one-way street for electricity? I mean, think about it. Current usually flows wherever it can, kind of like water. So how do you force it to go down one path and completely block it from coming back? Turns out, the answer is a really cool piece of material science.
All right, to build our microscopic one-way street, a plain old copper wire just isn't going to cut it. Nope, we need to start with a special class of materials called semiconductors. You've probably heard of the most famous one, silicon. And then we're going to mess with them a little bit. Or, as the experts say, we're going to dope them in two very specific ways.
Yeah, this whole tweaking process is called doping. First up, we create something called p-type material. We add these acceptor impurities, which leaves us with a whole bunch of what we call positive holes. Now, the easiest way to picture a hole is to think of it like an empty parking spot that's just waiting for an electron to pull in. Then, on the other hand, we create n-type material. We do that by adding different donor impurities. And that gives us a ton of free-roaming, negatively charged electrons.
Okay, so we've got our two custom materials, right? We have the p-type, which is full of those positive parking spots, and we've got the n-type, which is packed with free electrons that are looking for a place to park. Now for the really cool part. What do you think happens when we join them together?
The second they touch, this totally natural process called diffusion just kicks right in. All those free electrons on the n side, they see the empty holes on the p side, and they just rush across the junction to fill them up. And as those electrons are hopping from hole to hole on the p side, it basically creates the illusion of the positive holes drifting over to the n side. It's a chaotic little dance.
And this right here, this shows us that exact moment of contact. So on the left, in that p-type region, you see all the positive holes. On the right, in the n-type, you've got those mobile electrons. And that line right down the middle, that's the junction. Now, remember that crazy diffusion we were just talking about? Let's see what it leaves behind.
So the aftermath of this initial rush is really fascinating. As the electrons and holes meet up at the junction, they basically cancel each other out. They recombine and become neutral. But they leave behind their parent atoms, which are now charged ions that are totally locked into the crystal structure. This whole process carves out a zone right at the junction that is depleted of any free-moving charges. And so we call it the depletion region. Makes sense, right?
And here you can actually see that depletion region. Sometimes it's called the space charge region. Just look at how the n side of that junction now has a wall of fixed positive ions, and the p side has a wall of fixed negative ions. This separation of charge creates a permanent, built-in electric field that points across the junction. And that field is the whole secret.
You see, this built-in electric field is really the hero of our story. It acts like a barrier. You can think of it as an energy hill that any electron has to climb to get across. It actively pushes back against any more diffusion. And eventually, the initial rush from diffusion is perfectly balanced by the pushback from this barrier, and the whole system just settles into a stable state we call equilibrium.
If you're more of a visual person, this energy band diagram is another great way to picture that barrier. You can literally see the hill that the electrons on the n side would have to climb to get over to the p side. Without some kind of extra push, some extra energy, they're just stuck. We've done it. We have successfully built our one-way gate.
So, we've got our junction just sitting there, perfectly balanced in equilibrium with its built-in barrier. But what good is a gate if you can't open and close it? It's time to apply some electricity to connect it to a battery. In the world of electronics, this is known as biasing.
Now, we can connect our battery in one of two ways. If we connect the positive terminal to the p side and the negative terminal to the n side, that's what we call forward bias, and that's going to help current flow. But if we do the exact opposite, negative to the p side, positive to the n side, that's reverse bias, and as you might guess, it's going to block the current.
Let's start with forward bias. Okay, so we connect the positive end of our battery to the p side. And you know how charges repel? Well, this pushes all the positive holes towards the junction. At the very same time, the negative end of the battery is connected to the n side, and that pushes all the negative electrons also towards the junction. Everybody's moving to the middle.
And what does all this pushing do? Well, it directly fights against that built-in potential barrier we made. This external voltage actually shrinks the depletion region, it lowers that energy hill, and it gives the carriers just enough energy to start flooding across the junction.
And that flood, that flow of charge, well, that's exactly what an electric current is. The gate is wide open.
All right, now let's see what happens when we flip the battery around for reverse bias. We connect the positive terminal to the N side and the negative terminal to the P side. This time, instead of fighting against the barrier, our external voltage is actually going to help it to make it even stronger.
So the positive voltage on the N side starts pulling all the free electrons away from the junction, and the negative voltage on the P side pulls all the holes away from the junction too. This basically starves the boundary of any charge carriers, which makes the depletion region even wider and that potential barrier even higher. The gate just slams shut and pretty much no current can get through.
In this graph, the IV curve, this is like the diode's signature. It's the perfect summary of everything it does. See, on the right side, with a positive or forward voltage, the current just takes off. It goes almost straight up. But on the left side, with a negative or reverse voltage, the current is practically zero. That is the signature of a one-way street.
So after all that physics, what's the big picture here? What's the takeaway? Why does any of this matter so much?
The big takeaway is this. By cleverly doping two pieces of a semiconductor and sticking them together, we've created an electronic one-way valve. It lets current flow super easily in one direction, but it acts like a locked, closed gate in the other. And this simple, totally reliable control over electricity is pretty much the foundation for everything that came after it.
And its uses are absolutely everywhere. The most famous one is rectification. AC power from your wall flows back and forth, right? Well, by using a diode, we can just chop off the backwards half of that flow. That's the first major step in turning it into the steady DC power our electronics need to survive. Diodes also protect sensitive parts from getting fried by electricity flowing the wrong way. They really are the silent, unsung heroes in just about every circuit.
So there you have it, the diode's amazing one-way street, all built from just two simple layers of doped silicon. It's a valve. But that leaves us with a pretty tantalizing question, doesn't it? If we can build a simple valve with two layers, what happens when we stack three? What kind of even more powerful device could we create then? But that is a topic for another explainer.